In today's lecture, we are going to be learning about two new circuit elements, the capacitor and the inductor. So if you're unfamiliar with these circuit elements, you might ask, well, what is a capacitor? The most common implementation of a capacitor is what's known as a parallel plate capacitor, where we have two metallic plates and they're stacked on top of each other, like so. Typically speaking, there will be a material between the conductive plates. And this material is what's called a dielectric. Top plate and our bottom plate. So we have a sandwich-like structure, a top plate, a dielectric material, and then a bottom plate. This dielectric material is insulating, meaning that it's very difficult for current to pass through. So what a capacitor does is it's a form of temporary energy storage in circuits. So these plates collect electric charge. For every positive charge that gets collected on this top plate, a negative charge will get attracted to the bottom plate. Because the collected charge is separated by this physical barrier, the dielectric, an electric field will be established oriented from the positive charge to the negative charge, so down like so. And this electric field is, for all intents and purposes, potential energy. So we're storing energy inside this electric field by having positive charge, which I'll call Q plus, accumulated on the top plate, and negative charge, which I'll call Q minus, collected on the bottom plate. Now you may recall from your Physics 2 class that whenever you have charge separation, that means that there is a difference in electric potential, right? So there's a bunch of positive charge up here, there's a bunch of negative charge down here, and that creates a difference in electric potential between these two plates. That difference in electric potential is a voltage. So we would observe that there's going to be some voltage V across the plates, where the relationship is that charge measured in coulombs, charge Q is equal to the capacitance C multiplied by the voltage V. So we have Q is equal to C times V. From this, we can actually define the capacitance. Capacitance is then the ratio of the change in electric charge due to a corresponding change in voltage. Or C is equal to Q divided by V. So the capacitance of this sandwich structure is very dependent on the dielectric material and the geometry of the system. So for the parallel plate capacitor that we have drawn here, we can also see that C, the capacitance of this structure, is epsilon, the permittivity of the dielectric material, multiplied by A, the area of one of the plates, divided by D, which is the distance that separates the plates. So let me explicitly draw out these dimensions. Here is our distance. This guy has a particular width and a particular length. And this length times this width gives us this area A. Now, does it make sense that the capacitance depends on the geometry of the system? Well, think about it this way. A capacitor's job is to store charge. If we make this system physically larger by increasing the area, it should be easier for us to put charge on. So we should see that the capacitance increases. If we reduce this distance d, it should be easier to establish our electric field, which will then increase the capacitance. As far as the dielectric is concerned, that is a material property. So a vacuum has a dielectric constant of 1 multiplied by the permittivity of free space, whereas a silicon has a dielectric constant of 11.6 multiplied by the permittivity of free space, and deionized water is 81 times stronger than the permittivity of free space. So the material is going to matter, and the geometry is going to matter, and for this particular configuration, the capacitance is defined as such. So we are looking at capacitors in a circuits course. So now let's shift our attention a little bit to relationships that we could apply in our circuit analysis. So let's start by looking at the schematic symbols. In a schematic, capacitors are depicted in two ways. Here is our typical capacitor, which just shows that we have a terminal connected to a plate and then a plate connected to another terminal. So it is literally just a two-dimensional representation of our 3D sandwich structure. Our capacitance C would be here, and we see that capacitors obey the passive sign convention. So here's my voltage drop over my capacitor, and here is my current flowing into the positive polarity terminal of my capacitor. A second representation that you'll see a lot is this. So it's almost the exact same thing, but the bottom plate is curved. This is the schematic symbol for what's called an electrolytic capacitor. An electrolytic capacitor is a very special type of capacitor that has very, very small dielectric oxide layers. And in an electrolytic capacitor, if you apply a voltage of the wrong polarity, that very thin dielectric layer breaks down and effectively destroys the device. So it's a trade-off. You get very high capacitance values out of electrolytic capacitors because the dielectric layer is so thin, but they're very, very prone to misuse. You have to pay explicit attention to the way that you're connecting them, or you'll break them very easily. And an electrolytic capacitor obviously also follows the passive sign convention. So now, let's talk about our current voltage relationships. So we established previously that charge was equal to capacitance times voltage, and we know that current is equal to the derivative of charge. So if we take the derivative of the right-hand side of this equal sign, where we are assuming that our capacitor value does not vary with time, what we find is that the current IC of t is equal to C times dV dt. So this is our first relationship. Now, a common question regarding capacitor current is, well, how does any current flow through this device when there is literally a physical barrier preventing current from flowing from this top plate to the bottom plate? And the answer is, current doesn't really flow through the device, okay? So what I mean by that is, when we are moving charge onto the top plate, we are having some current directed down. So that would indicate that we have a positive current flowing into the device while charge just pools up on this plate. By the way, if we have current going into the device causing charge to pool up, we're going to see that the voltage is going to get larger and larger and larger. When we let charge move off of the top plate, then we have a negative current, a current in the opposite direction as what we have defined as positive. This is what's called a displacement current. So we don't actually have current passing through from one plate to the next. That would require what's called dielectric breakdown, which effectively destroys the capacitor. So normal operation, the current is just charge pooling and then charge getting released. Charge pooling and then charge getting released. So there is current moving, it's just not, which gives us there is charge moving, which gives us current. It's just not physically flowing from this positive top plate down to the negative plate. Our next relationship we can get by simply rearranging this guy. So if we divide both sides by C and multiply both sides by dt and integrate, we find that Vc of t will be equal to 1 over C integral from negative infinity to t of IC of t prime dt prime, where t prime is just a dummy variable that is representing time. So I have a t in my limits of integration, so I can't have a t down here. That's all that's happening. Now, it's pretty often to see this expressed in a slightly different form. So this is taking into account the entire history of the capacitor current. Instead, you'll often see this expressed as 1 divided by C integral from T naught. That's just a point in time at which the capacitor voltage is known, to T IC T prime dt prime plus Vc at t0. So now we have some initial condition on the capacitor voltage. This is the memory effect. And then we integrate from when we knew what voltage we had to some later point in time. And that gives us the current voltage on the capacitor. So these are our current and voltage relationships. We can now talk about power and energy. This is an energy storage device, so this is actually a very important topic. So fundamentally, the power absorbed by any electrical component, whether it's a capacitor or anything else, is simply the product of the current that flows through the device or component and the voltage drop that appears over the device. Since IC of t can be expressed in terms of Vc of t, we'll often see this rewritten as C Vc times the derivative of Vc with respect to time. So these are our power relationships. And energy, as always, is the integral of power. So we'll integrate from negative infinity to t. If we substitute in this relationship, that gives us the integral from negative infinity to t, and sorry, this should be t prime, of C Vc dVc by dt multiplied by dt, where these dt's cancel each other out. And we're now integrating with respect to dV. So at t is equal to negative infinity, we're going to assume that the capacitor voltage was 0. So Vc at negative infinity is equal to 0, and we're going to integrate up to Vc at time t of C Vc dVc, and again, under the assumption that Vc at negative infinity was 0, meaning at the beginning of time the capacitor didn't have any initial voltage over it, this reduces to 1/2 C Vc squared. So this is our fourth equation. Now, I've mentioned that the capacitor is a temporary energy storage device. And it may not seem obvious that having an electric field means that it's storing energy. So, hopefully you all remember that if we have a positive charge and we put it next to another positive charge, they repel each other. So, with that in mind, when we put our first charge on this top plate, it's pretty easy. But every subsequent charge we put on there, it gets harder and harder and harder, meaning that it's requiring work to put charge onto this top plate, to force those positive charges to be next to each other and stable requires work. Well, we're putting work or energy into the system. When we let those positive charges move off of the plate, that's releasing energy back into the system. So that's why having this electric field sustained is a form of temporary energy storage. We're forcing things to sit here using energy, and then when we let that go, we get that energy back, right? Energy can't be created or destroyed. So when we let the energy move off of the plate, obviously there was energy stored. All right. The last topics that we will talk about with regards to capacitors are how to combine them. We'll often see circuits where there are multiple capacitors, and so it will be useful for us to understand how we can combine them into an equivalent capacitance. So let's start combining capacitors. Let's start with a network where we have several capacitors connected in series. So here's capacitor number 1, which I'll call C1. Here's capacitor 2. Here is our nth capacitor. And we're going to assume that there is some voltage drop Vt over this network, and that there is some current It flowing into the network. So each capacitor will have an associated voltage drop. So this would be V1 of t, this will be V2 of t, all the way out to Vn of t, like so. And if we write a Kirchhoff's voltage law equation around this loop, we find that V of t is equal to V1 of t plus V2 of t plus Vn of t. Now, all of these capacitor voltage drops can be expressed in terms of this common current I. So for instance, V1 of t is 1 divided by C1, the integral from negative infinity to t of I of t prime dt prime. V2 is 1 over C2, integral from negative infinity to t I of t prime dt prime. And the voltage drop Vn is then 1 over Cn, integral from negative infinity to t I t prime dt prime. So we can see that there is a common factor of this integral in all of these parts of the right-hand expression. So if we factor that out, what we're left with is 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3, or excuse me, out to Cn. Integral negative infinity to t I t prime dt prime. And this looks like an equivalent capacitance 1 over Ceq, integral from negative infinity to t I of t prime dt prime. So from this, we can see that our equivalent capacitance is the inverse of the sum from k is equal to 1 to n of the reciprocals of our capacitance values. So effectively, this is extraordinarily similar to what we would see if we were combining resistors electrically connected in parallel. We add the reciprocals and then we take the inverse. This is the exact same thing we're observing here. So we can say that capacitors in series combine like resistors in parallel. If we instead have a lot of capacitors in parallel, call this C1, C2, C3. Again, we'll have some voltage over the terminals of the network, some current flowing into the network. We could observe that that current is going to split between the capacitors in some fashion. N. If we apply Kirchhoff's current law at our top node, we would see that I of t is equal to I1 plus I2 plus IN. We can express all of those capacitor currents in terms of the common voltage. Since everything is in parallel, they all share the same voltage. So this would be C1 dV dt plus C2 dV dt plus Cn dV dt, where we see that all of the terms have a common factor of the derivative of the voltage. So we can factor that out, leaving us with C1 plus C2 plus Cn multiplied by the derivative of the voltage. So that's our total current. And this, from the perspective of the current, looks like an equivalent capacitance, CEQ, multiplied by the derivative of the voltage, where the equivalent capacitance is simply the sum from k is equal to 1 to n of all of the individual capacitors that are in series. So, in parallel. So from this we can see that capacitors in parallel combine like resistors in series. So that's all I have for us on the behavior of capacitors for right now. When we come back, we'll talk about how inductors behave. Our next circuit element that we're going to be talking about today is the inductor. An inductor, in its most basic form, is comprised of a coil, or excuse me, a core. So we might see that as a cylinder of material, or a torus of material. And around these cores we wrap a wire which forms an electromagnetic coil. So this would be what's called a solenoidal inductor. here, this is what would be called a toroidal inductor. So in both cases, it's really just a section of wire wrapped around this core. Now the core here, it absolutely helps maintain the shape of the coil, but it's typically made of ferromagnetic material like iron. The reason we put iron inside of inductors is because iron is very easy to magnetize, right? And an inductor works by maintaining or observing magnetic flux. So inductors are another form of temporary energy storage in a circuit. And their energy is stored in an internal magnetic field. So in a capacitor, we saw that the energy was stored by an internal electric field. In an inductor, we'll see that it's stored by an internal magnetic field. So, hopefully a lot of you remember that if we have a section of wire and it's carrying some steady current I, let's say in this direction, we could use what's called the right-hand rule and see that this current I is going to generate a magnetic field, and that magnetic field is going to curl around the wire. So it's going to be going into the board, below the wire, and coming out of the board and circling back around. So we could write that, let's see, it's going into the board, so we would see the tail. It's coming out of the board, so we see the head of the arrow, like so. If we coil a wire instead of having a long straight wire, so for instance, if we passed some current I into our solenoidal inductor, we would observe that since the coil is going around this way, our magnetic field that's generated by the wire is going to be in the up direction. So we are going to have magnetic flux, which is just the amount of magnetic field divided by the area of the loop of the coil going up through this toroid. So the current creates this magnetic flux. That's called a flux linkage. That's the relationship. In our toroidal inductor, we would see, based on our right-hand rule, that since the coil is wrapped around this way, we'll get magnetic flux that circulates in a loop around our core, where the current I is in this direction. So, in these inductors, we observe that the magnetic flux which is just the density of the magnetic field, as a symbol phi b, is equal to the inductance, specifically the self-inductance L, multiplied by our current I. So our mathematical relationship is flux is equal to L times I. So from this, we can define inductance as the ratio of the change in magnetic flux due to a corresponding change in electric current. An alternative definition for inductance is that it is the tendency of a conductor to oppose a change in the electrical current flowing through it. This second definition comes from Faraday's law of electromagnetic induction, which states that an electromotive force, E, will be induced by a change in the magnetic flux with respect to time. For those of you who are unaware, an electromotive force is a force per unit charge that pushes charged particles around in a system. This perfectly describes the concept of what we know as voltage. Voltage is the work done per unit charge to move charge from point A to point B in the system. This electromotive force does the same thing. It's the push that causes currents to actually flow in the system. So we would see that our voltage is equal to negative the change in magnetic flux with respect to time, where this negative sign comes from Lenz's law. Lenz's law simply states that nature abhors a change in flux, so the voltage that's induced is trying to keep that flux constant. So if the flux is increasing, the voltage will be negative to try to cause the flux to go back down. If the flux is decreasing, the voltage will be positive to try to increase the flux back up to its original value. We're going to use Faraday's law to develop our current voltage relationships for our inductor, but we'll get to that in just a moment. All right, so enough elementary physics. In a circuit, an inductor is represented by this symbol. So it's just a coil, which is exactly what we see when we physically implement an inductor. It has some inductance L. If there is a voltage drop, VL over the inductor, then this guy will be absorbing power when a current IL flows into the positive terminal. So inductors also obey the passive sign convention because they are passive elements. They exhibit inductance whether or not voltage or current flows through them. All right, current voltage relationships. So as stated previously, Faraday's law of electromagnetic induction tells us that the voltage drop over an inductor, or the electromotive force, VL, is negative the change in magnetic flux with respect to time, where we know that magnetic flux is L times the inductor current. So from this we can see that the voltage drop is simply L dIL by dt. And our negative sign gets lost here. It's not intuitively obvious why, but it has to do with the fact that the voltage that's induced is in response to opposing the change in flux. So I did not make a mistake by leaving this negative sign out. Lenz's law is taking care of it when we go to this step. We can rearrange this expression, much like we did for our capacitor, and find that IL of t is 1 divided by L, integral from negative infinity to t, VL t prime, dt prime, or 1 over L integral from t naught to t, VL t prime, dt prime, plus IL at t naught. So again, t prime is a dummy variable that represents time, and this expression IL at t naught represents a known value of inductor current at some specific time t naught, so that we don't have to account for the entire history of the inductor current from t is equal to negative infinity up to the present. One thing that I would like to point out is that these equations should look very, very familiar at this point. Okay? What I mean by that, let's look at the expression for capacitor current. IC of t was C dV by dt. So this equation for capacitor current has the same form as the inductor voltage. This is because capacitors and inductors are what are known as electrical duals, meaning that they have the exact same relationships except that you have to transpose voltage and current. So we can get all of our inductor relationships simply by everywhere we see a voltage in our capacitor relationships, replace it with current. Everywhere we see a current, replace it with voltage, and everywhere we see a C, replace it with L. So that's just an interesting aside. You actually only need to know one set of equations and understand the concept of electrical duality, and you can get all of the other equations. Power and energy. Let's see. So power is defined to be the product of the current times the voltage, which is going to give us L I di by dt, substituting in this expression for the voltage. This is equation 3. And energy, as always, is the integral of power. those guys cancel each other out. And we're going to assume that the current flowing through the inductor at t is equal to negative infinity is 0. So this will be IL at negative infinity is equal to 0 amps. And we get 1/2 L times the inductor current squared. This is our fourth relationship. All right. So these are all the mathematical relationships that govern how inductors behave in a circuit. We may experience circuits that contain multiple inductors, so let's quickly go over how inductors combine. So if we have n inductors connected in series, this is inductor 1, inductor 2, inductor n, and there is some voltage drop, Vt over the inductor network, some current IT flowing into the inductor network, we would observe that there is a voltage drop over each inductor. So this is V1 of t, V2 of t, all the way out to Vn of t. Applying Kirchhoff's voltage law around our loop, we would find that V of t is equal to V1 plus V2 plus Vn, where we can express all of our inductor voltages in terms of this common series current I of t. So that would be L1 di by dt plus L2 di by dt plus L3 di by dt, where we see that all of these terms on the right-hand side have a common factor of di by dt. So if we factor that out, we're left with L1 plus L2 plus this should be n. Di by dt, which from the perspective of the voltage means that we have some equivalent inductance, LEQ times the derivative of the current, where LEQ is simply the sum from k is equal to 1 to n of all of the inductors connected in series. So we can see that inductors in series combine like resistors in series. If we have n inductors connected in parallel, L1, L2, all the way out to Ln, there is a voltage V of t over the parallel network. There is a current I of t flowing into the parallel network. We should see that that current I of t splits among the inductors. So this would be I1, I2, all the way out to IN. Performing Kirchhoff's current law at the top node gives us I of t is equal to I1 plus I2 plus IN, where we can express all of those inductor currents in terms of this common parallel voltage V of t. So this will be 1 over L1, the integral from negative infinity to t, V t prime dt prime plus 1 over L2, integral from negative infinity to t, Vt prime dt prime plus 1 over Ln, integral from negative infinity to t, Vt prime dt prime. So everything has a common factor of the integral of V of t. So we can combine like terms and we get 1 over L1 plus 1 over L2 plus 1 over L3, integral from negative infinity to t of V t prime dt prime, which from the perspective of the current entering the network looks like we have an equivalent inductance 1 over LEQ multiplied by the integral of V of t prime dt prime, where our equivalent inductance LEQ is the inverse of the sum from k is equal to 1 to n of the reciprocals of our inductors that are connected in parallel. So we see that inductors connected in parallel combine like resistors connected in parallel. That's all I have prepared for understanding and developing the relationships for inductors in circuits. When we come back, we will work a few example problems to help illustrate circuit analysis with these components. This is the first example problem we're going to work that contains capacitors and inductors. We're asked to find the total energy stored in this circuit, meaning that we need to find the energy stored by inductor L1, the energy stored by inductor L2, the energy stored by capacitor C1, and the energy stored by capacitor C2, and add them all together. One thing that I would like to point out here is that this is a circuit that is at DC steady state. And I can see this because I only have a single source in the circuit, and it is a DC source. So what does the concept of DC steady state mean? Well, if my excitation is a DC term, like this voltage source, then that means that all of my voltages and all of my currents in my circuit will also be DC or constant quantities. Now this is a very important concept with regards to circuits containing inductors and capacitors. Alright, so for an inductor, we know that the voltage drop over an inductor, VL, as a function of time, is equal to the inductor value L times the derivative of the inductor current with respect to time. If we know for sure that all of our currents are going to be DC or constant quantities, then this derivative goes to 0, and that means that the voltage drop over our inductors by definition will be 0. So we're going to replace all of our inductors with an electrically equivalent circuit element that forces the voltage drop to be 0, which in this case would be a short circuit. So we're going to replace all of our inductors with wires. Because we know that the voltage drop over a simple wire is 0, while allowing any amount of current that needs to flow through it to flow through it. Similarly, the current through a capacitor is C multiplied by the derivative of the capacitor voltage with respect to time. Well, if the voltage drop over the capacitor isn't changing, this derivative term goes to 0, and that means the current flowing through the the capacitor must be exactly equal to 0. So we will be replacing our capacitors with an electrically equivalent circuit element that does not allow any current to flow through it, or an open circuit. So I'm going to modify my original circuit diagram to reflect these DC steady state equivalents. Now, I want to be very, very clear here. I am not removing my capacitor from the circuit or shorting out my inductor. I'm simply saying that they behave, like the inductor will behave like a short circuit at DC steady state, and a capacitor will behave like an open circuit at DC steady state. So, this 2 Henry inductor is going to behave like a short circuit, and this quantity will be the current through that 2 Henry inductor. This 10 millifarad capacitor will behave like an open circuit, and I'm going to assign this polarity to the voltage drop over that capacitor. For our 6 Henry inductor, again, I replace it with its electrical equivalent, and I'm going to look at the current. And for this 20 millifarad capacitor, I'm going to replace it with its electrical equivalent, and I'm going to try to determine the voltage drop over it. The reason why I've specifically identified inductor currents and capacitor voltages is because the energy stored by an inductor, WL, is 1/2 L times the current in the inductor squared, and the energy stored by a capacitor, WC, is 1/2 C times the voltage drop over the capacitor squared. So if I can figure out this current, I can easily determine how much energy is stored by this inductor. If I can determine this voltage, I can easily determine how much energy is stored by this capacitor. And the same thing for our other inductors and capacitors in the circuit. So, let's start with probably the easiest quantity to determine, which is IL1. So we see that we have a short circuit in series with an open circuit, and by definition, no current can flow through the open circuit. So IL1, by inspection, must be 0 amps. Which means the energy stored by the inductor L1 is 0 joules. So that one was pretty easy. The next easiest thing might be the inductor current IL2. So let me explain why I think that that's the next easiest quantity to determine. This voltage source is going to output some amount of current. It's going to flow through that 5 ohm resistor, and then it's going to flow into this node. At this node, it can split in 3 different directions. It can flow to the left, it could flow up, or it could flow right, and some portion of it may flow in all of the directions. Now, we have just established that IL1 is equal to 0 because there's an open circuit. So this current sees this open circuit and says, well, I can't flow this way. It sees this open circuit on the top and says, I can't flow this way. So all of that current must flow through the 6 ohm resistor, flow through our inductor, flow through the 4 ohm resistor, and it just makes this simple loop over and over and over again. So from that, IL2 is going to be the voltage drop, 30 volts, divided by the total series resistance seen by the current. 5 ohms plus 6 ohms plus 4 ohms looks like 15 ohms to me. So our inductor current IL2 is 2 amps. The energy stored by inductor L2 is 1/2 times 6 Henry times 2 amps squared. So that's 3 times 4 is 12 joules. All right, now we need to figure out VC1 and VC2. And I think VC2 is a little bit easier. The reason I say that is that VC2 is going to be the same as the voltage drop over this 6 ohm resistor. The positive polarity terminal is connected to the left-hand leg of the 6 ohm resistor. The negative polarity terminal is connected to the right-hand leg of the 6 ohm resistor. So because this inductor looks like a short circuit, our capacitor voltage is effectively in parallel with this 6 ohm resistor. So from that, we can see that VC2 is equal to 6 ohms times the current flowing through our 6 ohm resistor, which we just established to be 2 amps, is 12 volts. And so we will have WC2 is equal to 1/2 times 20 millifarads times 12 volts quantity squared. And I believe this gives me 1.44 joules. That's correct. Lastly, we have to determine the voltage drop over our capacitor C1. And for this one, I'm going to use Kirchhoff's voltage law. I'm going to start at this bottom left-hand corner and work my way around the circuit like so. So that's the orange is the loop I'm taking to write my KVL equation. So I would see negative 30 volts plus 5 ohms times the current that's flowing through that 5 ohm resistor, which is 2 amps, plus 10 ohms times the current which is flowing through the 10 ohm resistor, which we know to be 0 amps, plus VC1 is equal to 0. So I can rearrange this and find that VC1 is equal to 30 minus 10 is 20 volts, and thus the energy stored by capacitor C1 is equal to 1/2 times 10 millifarads times 20 volts squared, which gives me 2 joules. Lastly, because I want the total energy stored, that is going to be W total is the energy stored by the inductor L1 plus the energy stored by the inductor L2 plus the energy stored by capacitor C1 plus the energy stored by capacitor C2, which is 0 plus 12 plus 1.44 plus 2, which looks like, let's see, 12 plus 2 is 14 plus 1.44, 15.44 joules. So we've analyzed our first circuit containing inductors and capacitors. Our next example, we will increase the level of difficulty a bit by not operating at DC steady state. In our next example problem, we are trying to determine a mathematical expression for the voltage drop over our current source, Vs of t. We know what the current provided by the source is, and we are also told that the voltage drop over the capacitor with this polarity at t is equal to 0 is 5 volts. So we are going to approach this problem using simple circuit analysis techniques. We're no longer at DC steady state, so we can't just arbitrarily say, well, this guy's going to look like an open circuit and this guy's going to look like a short circuit and try to make our lives easier. It can't be done because this source is not a DC source. It varies with time. It's 40 milliamps exponentially decaying at a rate of negative 800 units per second. So what we're going to do is we are going to apply Kirchhoff's voltage law. So I'm going to define my resistor voltage, positive polarity on the left so that the current flows into the positive polarity terminal, and I'm also going to define an inductor voltage, VL of t, positive polarity on top, so that the inductor current flows into the positive polarity terminal. So if we write the Kirchhoff's voltage law equation, we can see pretty easily that Vs of t will simply be Vr of t plus VL of t plus Vc of t. Okay? Now, Vr of t we can get using Ohm's law. We know the resistor value and we know the current flowing through the element. So using Ohm's law, Vr of t is going to be R times Is of t, which will give us 1 kiloohm times 40 e to the minus 800 t milliamps. So this will look like 1 kiloohm times 40 milliamps is 40 volts. So 40 e to the minus 800 t volts. So we've got one of our three contributors to Vs already. For our inductor voltage, VL of t will be L times the derivative of the inductor current, which in this case is Is of t as well. So L is 1/4 of a Henry, where a Henry is a volt second per ampere. When we take the derivative of this 40 e to the minus 800 t milliamp guy, with the derivative of an exponential function, we're going to take this negative 800 down. So that's going to be negative 800. And it has units of per seconds because it's multiplied by time. So I'm going to put seconds to the negative 1. And we see that seconds multiplied by per seconds, those guys cancel each other out. Then we're going to have 40 milliamps. So that is 40 times 10 to the minus 3 amperes, where this amp cancels this amp, e to the minus 800 t. And so dimensionally, as far as units go, we're left with volts. So we simply multiply all of those guys together, and we get that that is negative 8 e to the minus 800 t volts. So fairly straightforward, just understanding how to use the derivative operation for an exponential function and being consistent with our units. Our capacitor voltage is going to be a little bit more difficult, at least to me, because it has an integral in it, and I'm notoriously bad at integration. So Vc of t is 1 over c, the integral from t naught, some point in time where the value of the capacitor is known, to t of the capacitor current, which is Is, of t prime dt prime, plus some initial condition on the capacitor voltage, Vc at t naught. So we're going to have 1 over 10 microfarads so 10 times 10 to the minus 6 is a microfarad, where a farad is an amp second per volt. So I'm going to have amp seconds in the denominator, 1 volt in the numerator. So that's my 1 over c term. I'm going to integrate from t is equal to 0 to t of my 40 times 10 to the minus 3 amps e to the minus 800 t prime dt prime plus my initial condition, which I'm told is 5 volts. So when I integrate an exponential function, I'm going to have 1 over negative 800. So this is going to look like, this is going to stay the same, 10 times 10 to the minus 6 amp seconds per 1 volt. This is a constant term, so it can get pulled out. So that's going to be 40 times 10 to the minus 3 amps divided by negative 800 per second. That's from integrating this guy, where the amps cancel, seconds multiplied by per seconds cancel. The result of this integration is going to be e to the negative 800t minus e to the negative 800 times 0. So that's going to be e to the minus 800t minus e to the 0 is 1. And to this, I'm going to add 5 volts. And I'm running out of room here, so I'll try to sneak it in. So this 40 times 10 to the minus 3 divided by 10 times 10 to the minus 6 times negative 800 gives me 5 e to the minus 800t. So 5 times e to the minus 800t minus 1 plus 5 volts. Combining all of that, I get 10 volts minus 5 e to the minus 800t volts. So finally, I need to add all these terms up. So I have only one DC term, 10 volts, so I'm going to go ahead and tack that on. And then I have 40 minus 8 minus 5, so that's 40 minus 13 is plus 27 e to the minus 800t volts. And that is the voltage provided by my source. Alrighty. Well, thank you guys for watching. If you have any questions, feel free to email me at hartman@lawtech.edu or comment or whatever. Thanks.